So the last time we began talking about lipids, we said they were molecules with either a single hydrocarbon tail or a double hydrocarbon tail. The top of this molecule, or the head, tended to be polar, and the tails, or hydrocarbon tails, they're non-polar, and they tend to be hydrophobic. Whereas the head is polar and hydrophilic. And many of the properties of these molecules in aggregate can be understood just from the fact that they're really made up of two parts. One part which likes water, and one part which dislikes water. The reason that these molecules dislike water is a kind of subtle reason. The reason is that these tails tend to disrupt the ordering of water, the hydrogen bond network of water around them. And because they do that, so it's not really, it has to do so much with energy as with the fact that it reduces the entropy of the water, and therefore it's not thermodynamically favorable. That's a somewhat subtle reason why these hydrocarbon tails don't like water. Then we spoke a little bit about the different forms in which these molecules could appear, and one form was a form that looked like this, in which all of these heads pointed outwards towards the water, and all the tails were insulated from the water, essentially seeing only a hydrocarbon environment made up of themselves. This we called a micelle. You could have other more complicated arrangements, and one arrangement is this, where you have the molecules arranged as they were in the micelle. But the larger scale arrangement, so here are heads all over the place around here, but at larger scales they organize into cylinders. So this is called a cylindrical phase. Then we had the bilayer phase, where the molecule formed two layers. Bilayer because each of these is one layer on its own. So this is a bilayer phase. And the bilayer membrane allows you to have both water on the outside as well as on the inside of the membrane. And this is a preferred arrangement. The bilayer construction is a useful way for the cell to compartmentalize the inner parts of the cell from the outer parts of the cell. Okay. The last was homogeneous or disordered. And that was a state where all of these molecules more or less moved about independently in solution without forming any macroscopically structured phase such as the micellar phase or the cylindrical phase or the bilayer phase. And there's some part of research which goes into taking molecules of this form, that amphiphilic, they may have one leg, two legs, they may have more complicated behavior here. You could have charges, say plus or minus on the head group specifically. You could have charges on these tails as well, and ask what are the structures that form here? Do you have the same sorts of structures, or can you have more exotic types of structures? What is the nature of the transitions between these structures? These are all questions that are of interest to people who work in soft matter, but are not very relevant from the biological point of view. What is relevant, however, is a couple of definitions which we described the last time. And one of these definitions was what we call the critical micellar concentration. And that was the concentration, let us say rho star, below which, so this is the CMC, so for densities rho less than rho star, it preferred the disordered or homogeneous arrangement in which each of these tails were exposed to the solution. And on this side here, for rho greater than rho star, it prefers some sort of ordered or structured configuration in which the tails were not exposed to the solution. Okay? And then we thought we would try to estimate this. The way we estimated it is, again, so let me fill in some of the details that I missed out the last time. We said, let us imagine that these can either be in a configuration where all these tails are protected from each other. Let us ignore the entropy of this configuration. Let's just assume that we only need to worry about the energetics of this configuration. So now what one can do is to take a molecule from here and try and move it outside. Once it goes outside, it has a lot of entropy because it can be here or here or here or here, but it loses energy. It loses the energy by virtue of the fact that here these tails are protected from the aqueous solution, but now these tails are not protected. So then we tried to estimate how much energy that would take. So we said, let us imagine that now that this is my 0th energy solution. So if I take this out, I pay an energy, but I gain an entropy. How much energy do I pay? Was the question. So then the way we answered that was to say that, look, think of this molecule or the tails of these molecules as forming a cylinder. Okay? And this cylinder has a radius of r, hc for hydrocarbon tail. Okay? It was made up of Nc carbon atoms and Lcc was the distance between adjacent carbon atoms. So a measure of the length of this cylinder is Nc times Lcc. So the surface exposed, when I take a molecule from inside and put it outside, that is Nc times Lcc times 2 pi times r, hydrocarbon tail. You agree with that? So if this is the surface exposed, the energy is obtained by taking the surface exposed, Nc, Lcc, 2 pi r hc, and multiplying it by some energy per unit length, or energy, force per unit length, or energy per unit surface. Okay? This is the surface over here because it's the length times the length. This is a surface tension which comes from exposing the hydrocarbon tail to water outside. There's an energy cost in that, and that cost depends upon how much energy I pay, depends upon how much surface I expose. And so this is some energy per unit surface, positive. So this is also called a surface tension. And this here was the energetic term that we had to worry about. And I think we called it the binding energy. The second part of the argument said, let us see, you have paid energy in order to come out here, but I have gained entropy. Can I count that entropy? And in order to count that entropy, we said, suppose we can evaluate the free energy. Since the free energy is the internal energy minus the temperature times the entropy, then from here I can get the entropy is E minus F divided by T. So if I could calculate my free energy, I know if I could calculate my energy and divide this combination by T, then I get the entropy. Or equivalently, I really need Ts because that is what enters my free energy. So just E minus S. Okay? This is the binding energy for a single molecule. So it's the binding energy per molecule, you can say. If there are n molecules outside, I have to multiply this by n to find the total energy cost. Similarly, I want to evaluate the entropy term in order to insert it into the form T times S and find what is the entropy per particle. So to do that, remember that we calculated the partition function z initially, and we found that z was v to the power n divided by n factorial lambda to the power 3n, where lambda took the form h squared, so h over square root of 2 pi m kb. From here, I got f equal to minus kbt times log of z, and I said the energy E is of course just 3/2 of n times kb times t. So I have all the ingredients that I need in order to find out what is the F and what is the energy. Okay. So from here, my F is just n times kbt into rho lambda cubed minus 1. That's how to calculate it. Then we had to add this particular term to it as well. So now, since my zero of energy is a completely bound state, that the way I can estimate what is the competition between the energy gained due to being in that confined state versus the entropy gain to being separated is just obtained by setting E binding to be approximately equal to the entropy term T times S. So this is a condition. If E binding term is very large, then I will always tend to be bound because I pay too much energy to be unbound. If the term here, if on the other hand it is small compared to this term, then the entropy will always win out, because it's always favorable to let these molecules go around because I gain so much of entropy from that. So from here, if I put all of this back in, put the rho lambda cube term in, etc., I get rho times lambda cubed is exponential of, and the term that I had was 5/2 minus E binding divided by kbt. And this was my basic result that I got from the last time. Should be in your notes from the last time. There was a here. No, I think that's correct, right?
So F equal to n kbt into log rho lambda.
Here, this one? Here. Yeah, sorry, my fault. That should be there, correct. Yeah. Yeah, I don't need an n here because it's already there hiding inside the z. Okay? So this sets the critical density, the rho, for my particular value of the critical micellar concentration. So now, if I tell you what all of the terms are inside this E binding, if I tell you what lambda cubed is, if I tell you what the temperature is, etc., you should be able to calculate the rho star from here. So rho star is just e to the power 5/2 minus E binding divided by kbt times the factor of lambda cubed. Okay? So let's just calculate a few parts of this. Let us try and calculate the value of lambda first. So lambda is h divided by 2 pi m kbt to the power 1/2. Okay? So first of all, h is 6.6 into 10 to the power minus 34 in MKS units. What appears in the denominator is a factor of 2 pi, which is 6.28. And now what we need is to understand what is the mass of these molecules, which really is concentrated in the chains, not so much in the head group in this particular case. So the mass is something like 600 Dalton. So let us say into 600 for the mass, and the conversion between the Dalton and the kilogram is that I have to multiply this by 1.66 into 10 to the power minus 24 to get it into the proper MKS form. Then I have to multiply that by Kb and multiply that by T. So this is into 1.38 into 10 to the power minus 23, which is a Kb part, into the temperature, which let me say is around 300 Kelvin. So can you just quickly try and estimate this? Just see how one would do it. Let's pull out all the factors, the irrelevant factors. Let us say I have 10 to the power minus 34 at the top.
The mass is for one phospholipid molecule.
The mass is for the full thing, for the full case. It doesn't matter. It's only, even if it is, it's only a factor of 2. But over here, this mass is for the full molecule, as I remember it, around 600 to 700 Dalton. Okay. So over here in the numerator, in the denominator, I have square root of 6.28, then a square root of, let us say, 6 here, I take that out, into a factor of 1.38, into a factor of 3 from the 300. And what I have left over is the 10 to the power 2 that comes from here, a 10 to the power minus 24 that comes from here, a 10 to the power minus 23 which comes from here, and a 10 to the power 2 which comes from the last term. Okay. Now we can go back and put all of that back in. Having done that, what we will get is 10 to the power minus 34, some number that sits out here which I have not yet calculated, and a square root of now 10 to the power something. But what is that something? So, did you calculate that? So 10 to the power 2 and 10 to the power 4, this becomes 10 to the power minus 19, minus 43, minus how much?
Minus 43.
Minus 43. Let us try and estimate this number that sits here. That number must be square root of 6.28 into 6 into 1.38 into 3, which is, let us say, 18 into 6 roughly. 18 into 6 roughly is 10 to the 2. So that is 1 over square root of 10 to the 2. Is that correct? Roughly. So then this makes it a little easier for me to calculate, because then this becomes 10 to the power minus 34 divided by square root of 10 to the power minus 41, let us say minus 40, and this would be 10 to the power minus 34 into 10 to the power, let us say 20 odd here, which is about 10 to the power minus 14 roughly. And I have a somewhat slightly larger number here, which I think I did when you, first of all, we changed one factor of 10 here, so the square root of 10 that sits there. This is the other factor that sits outside. What I have is something like more like 10 to the power minus 12 is the right answer. I think it's 6 or 7 to 10 to the power minus 12. You can just check that. It's just there for approximate reasons. So that means we have now got our lambda cube term. then we need to worry about these other factors here. So the E binding so let's just calculate the E binding part, which we said was, okay, I've now rubbed it out, but that was a factor of 2 pi times R HC. And R HC, let us say, a good approximation for that is around 0.3 nanometers. Then we have NC, and a good approximation for that is, let us say, 15 carbon atoms in a chain. And NC times LCC, let us say the combination of NC times LCC is still a length. And this particular combination I have in my notes is about 1.26 nanometers. Okay? Is that all right? So now can you just estimate what this is? And then we have finally, we forgot our gamma. And the good value for gamma is around 0.05 joule per meter squared. Again, that goes back to giving you the answer. Okay. Can you just quickly try and estimate what this is? You have to worry about all the factors of nanometers. They'll be 10 power minus 9 meters. So if you want, we can just try again. This is 6.28 into 3 into 10 to the power 0.3 nanometers is 3.3 into 10 to the power minus 9, which is 3 into 10 to the power minus 1 into 10 to the power minus 9, which is 3 into 10 to the power minus 10 from there. Then I have a factor of 1.26 into 10 to the power minus 9 into 0.05. And if I've done everything right, the units should all be correct, and I would have done this carefully enough. So let us say 6 into 18 to 1 roughly, okay. Even 0.05, let me just multiply by 5 and multiply by 10 to the power minus 2. So that becomes 5, 6 5s are 30, about 100, let us say, 10 to the power 2 that comes from here, 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 and here. Okay? Multiply this by 10 to the power minus 10, multiply this by 10 to the power minus 9, multiply this by 10 to the power minus 2, which is, so now this and this will go. This is approximately 10 to the power minus 19. And the unit should be joules, approximately. And we know that kBt is approximately, let's say, 0.024 electron volts, which is approximately 0.024 into 1.6 into 10 to the power minus 19 joules. Okay. So then I have a number which is about 10 to the power minus 19 and 10 to the power minus 19 here. The only distinction is a small number that sits over here. So what you should get is E binding divided by kBt is approximately a factor of about 30. So given that, we can now put that back and let us see. I haven't actually done this before. We're doing it on the board, so we have to make sure that we don't make any mistakes in our calculation or in the assumption that we've actually made. And so let us just have a look at this. So I get 10 to the power minus 19. So the inverse of this of roughly 1.6, it should be about right, I think. Now remember that rho was 1 over lambda cubed e to the power 5 by 2 minus E binding divided by kBt. If E binding divided by kBt is about 30, then this doesn't matter so much. It's this term that dominates. 5 by 2 is relatively small. Okay. So then I have approximately e to the power minus 30. And what was the number that we had for lambda? 10 to the power minus 12. So when I raise lambda to the third power, that becomes 10 to the power minus 36. Okay. Now e to the power minus 30 is not something that I can remember offhand, unless one of you can remember it offhand. So how would one do that? What is a good way of doing it? Okay, I mean it's not a very good way to approximate E by 2. But in principle, that could have been possible, that we approximate E by 2, right, 2 to the power minus 30, and 2 is 10 to the power 0.3. So that becomes 10 to the power 0.3 times 30, which is some number like 0.10 to the 9 or something. And then that would go away with this particular factor here. So just do it. Go back and just try it out. The only number that I would sort of finally like you to get is something like the density for aggregation on this rho star is approximately 10 to the power (22) per meter cubed, and that's about 2 into 10 to the power minus 5 moles. Okay, so that's just how, and these are not unreasonable values in terms of the real system. Okay, let's now go back a little bit to try and thinking about the shapes of molecules. As I said, these molecules can come in interesting shapes. One is a shape that is, say, looks like this, where the head is much smaller than the area that is taken up by the tail, which is much larger.
What is lambda actually?
Lambda is called the thermal de Broglie wavelength. I'll just write it down. It's a quantity that enters when you calculate the partition function. Because it involves the Planck's constant h, there is some quantum mechanical meaning to this. But it's not worth explaining at this level because it's not very useful. It's just a useful length that tells you, okay, so I can explain a little bit about what it is. It's like a wavelength, as the name suggests. And the idea is that all these particles have some quantum mechanical wavelength that is associated with that.
Vibrating.
Huh?
Is it vibrating?
It's not vibrating. It's just any particle with some momentum p has a wavelength lambda which is h divided by p. And in a sense, because it's at finite temperature, it always has some average momentum associated with it. And this is a way of estimating what is that momentum, and from there what is that lambda. Now the lambda that it has is some measure of over what region are quantum mechanical effects important. If these particles are very well separated, so that they are separated by a distance that is much larger than lambda, then effectively these are like point particles. And I can think of them, treat them as I did classically, completely as point particles. But once they become much closer than the distance lambda, which is the distance finally, that means I should worry a little bit about quantum mechanical effects. That's essentially what it means. It's a way of telling you when is quantum mechanics important and when is it unimportant. Okay. The other type of shape is one that is far more cylindrical. So it might look like that. And of course, the opposite limit is where you have a large head and a small tail. So maybe it would be something that actually looks a little more like an inverted cone. So let's just look at what might be favored, what structures might be favored by different shapes of molecules. So let's consider a spherical micelle. So that's something that looks like let this micelle have some radius r. So that means the area is 4 pi r squared and the volume is 4 by 3 pi r cubed. Let the average surface area, which is this part of it, of a molecule be A0. Okay? Second, let the volume of the hydrocarbon chain, such as this part, be something called nu. Okay? And in my notation, I have nu sub hydrocarbon, sub Hc. So one condition is that if all of these molecules are to pack tightly into forming a spherical micelle, then the number of molecules that have to do that are obtained by taking the surface area 4 pi r squared and dividing it by the area of one of these. So this is the number of molecules. If I take the total surface area here and divide it by the area that is occupied by one of these molecules, I should find the number of molecules inside. But this also has to be consistent with the fact that if I take the full volume, the 4 by 3 pi r cubed, and I subdivide that into the volume occupied by all of these hydrocarbon tails, these numbers should be the same because they're counting the same thing. They're counting the number of molecules inside. So 4 by 3 pi r cubed times nu Hc, these two numbers should be the same. So now let us get rid of factors of 4 pi, factors of r, and so on. And then we find that if, let us say, r A naught divided by nu hydrocarbon is 3, then 3 or 1 by 3. Yeah, that's correct. I'm just trying to see whether I have. Yeah. The only other condition that I need is that R here must be the length of the hydrocarbon tail. Okay? Because it can't, otherwise it would expose further amounts of the liquid too. So length of the hydrocarbon tail times A naught divided by the volume V of the hydrocarbon tail. This should be about 3. And in fact, the way this condition is usually written is to say nu Hc divided by L Hc A naught should be less than 1 by 3rd is the condition for a spherical micelle. The less than or approximately equal, less than or equal to, is the condition such that I can pack it maybe tighter, but I can't pack it looser. Okay? Let's now go and think about the cylindrical state. So here is cylinder. Here are the molecules that are attached to the cylinder. And I do the same thing. I know that the surface area of the cylinder is 2 pi r times the thickness, let us say. So let this be the thickness T. So the surface area is 2 pi times r times the thickness T, and the volume is pi r squared times the thickness T. So similarly, I take these factors 2 pi r t and then I divide that by the number of, by the area of each of these heads. This must be equal to the term on the right hand side, which is pi r squared t, divided by nu, the volume occupied by the hydrocarbon tails. I can now simplify this, getting rid of t and t, getting rid of pi and pi, taking an r and putting just an r there. And what I will get is something as I had earlier. So instead of r, I can again call this L for the hydrocarbon tail. What we will get is something that looks like nu hydrocarbon divided by length hydrocarbon times A naught should be between 1/3 and 1/2 for this state, for the cylindrical state, to be stable. This is the lower bound because below this particular state is stable. Okay? Finally, it turns out that the bilayers, and we won't do this particular calculation, for the bilayer, this particular shape parameter, the nu hydrocarbon divided by A naught L HC, should be between a half and a 1. Okay? Essentially the same sorts of arguments. For these, you would like to pack it like this, with the molecules in this direction, and you would like to pack it fairly tightly. Okay, so this is just simple arguments about what is the phase, and the only reason to do all these arguments is just to illustrate the use of simple qualitative arguments, to tell you how exactly the shape or the structure that you form depends upon some basic geometrical features of that phase. And before that, the argument that we need to do is how to calculate a critical micellar concentration, and therefore how to begin to be comfortable with arguments that compare an energy with an entropy, how to compare the entropy. The idea of taking entropy from its ideal gas form makes the calculation very simple. I don't have to do complicated calculations for that. And so this is a good ballpark understanding of the figures that are involved, or the numerics that are involved, to set this up. So now let's just go back again to thinking about surfaces in a little more general way. And before we do that, let's just sort of remind ourselves that we were thinking about lines or polymers or filaments in three-dimensional space. And for that, I had to specify some vector r as a function of some internal coordinate, which I might have called u. So u might be the distance between adjacent carbon atoms or something along this particular chain. So if I asked what exactly is the physical distance between 2 points here and here, let me call this u1 and let me call this u2. That physical distance is mod of r of u1 minus r of u2. It's mod because it is actually a distance. As I make this come very close to this, what I will have is this particular distance then becomes dr by du mod times the factor of du. Okay, this is just saying that this is just a derivative times this particular object du. So let us call this an internal distance ds, because now this initial u could be anything that I used in whatever region. It's just that with every u I must smoothly associate a point along this particular chain. On the other hand, s has a specific meaning. S is the arc length. It's a distance measured along the chain. So if I integrate the total length between 0 and L of ds, this must give me the length, the full length of the chain, because it's actually doing a physical measurement. It's if I stretch this out, this would actually physically measure what is the distance between this point and this point. Okay. So the vector t hat, which is dr divided by ds, which would be dr by du, ds by du. Okay. This particular quantity here. You can check that dr by du divided by ds by du is actually normalized to 1. By the way, this should be dr, there is no mod there. Dr by du divided by ds by du, which is why I have written a unit vector t hat. So once I go to describing things in terms of this internal coordinate ds, so s is now an internal arc length coordinate. Once I do that, then this vector t hat defined as dr by ds is automatically normalized and becomes a unit vector. So this is the vector that we were worried about earlier when we were thought about semi-flexible polymers. We said we wanted to look at polymers whose length was a constant, and we wanted to describe the energy cost for deforming it. So we said the simple way of doing it is to take these tangent vectors and say that the moment these tangent vectors began to change, there was a difference between the configuration in which they were all parallel to each other, just like this, a straight rod. Deforming away from this rod cost me an energy. So we said that energy came from Lp here divided by 2 integral 0 to L ds of the change of this tangent vector dt hat of s with respect to s squared. So because it's a change of tangent vector, something that is curved like this, we'll see a tangent vector here, 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 here. It's changing as we move across inside this internal space that is parameterized by S. Okay. Now we want to think a little bit about how to describe membranes, because it's certainly a more complicated picture than just a simple one that I showed you here with a simple polymer. The difference between the membrane and the polymer is that now I have some coordinate that tells me where the membrane is, which is r, which is a function not of one quantity u, but of two quantities u. So it's a function of, say, u1 and u2, or let me just say u and v. This is the difference between describing a filament or a polymer and describing a membrane. I still have a vector r that tells me where is the structure that I'm looking at. This is r. The only difference is now that it is a function of two variables, u and v. We described the last time a particularly simple way of parameterizing this. And I even gave you the name for it, that was called a Monge gauge. Just the word gauge is just a somewhat technical term that we really needn't worry about at this point. So this says I can describe my vector r by saying, given an x coordinate, given a y coordinate, I can tell you what is the height of the surface for that particular x and y. So this is a Cartesian basis because x and y point along two perpendicular directions. So this is a Cartesian description. But on the other hand, it need not have been at all, because I know that anything I need to do to describe membrane is just to supply 2 coordinates here. And this r must vary smoothly as I vary those internal coordinates. So for example, if I was looking at something that was, say, a membrane that was wound around in the form of a circle, I might find it more simple to just describe this membrane in terms of some point indexed by theta and phi on that membrane, on that surface. So by just telling you what is the radial r as a function of theta and phi, I have actually told you exactly the same information contained here. It's just that these u and v are now replaced by theta and phi. As before, I need 2 variables, the third variable is then fixed by the requirement that it is a membrane. It's even more interesting that even x and y need not even be perpendicular to me. There could be some strange coordinate system that I choose for convenience. And the requirement that the physics should not depend upon what is my choice of x and y or my choice of coordinates is a very deep mathematical requirement in the theory of surfaces, which we won't describe. I just wanted to understand that physically. That because we want to describe configurations of molecules that can move smoothly with respect to each other, it's a fluid membrane. So these molecules are diffusing, but nevertheless they retain the integrity of a surface. For that reason, any way, whichever way I have of describing the surface, they should all be equivalent. Whether I use periodic boundary conditions, whether I use spherical polar coordinates or Cartesian coordinates or some other coordinate, I'm still describing the same surface. So any way of calculating the energies, etc., must be independent of the way that I describe that surface. I should not write down an expression that is valid only in Cartesian coordinates, because you may not use Cartesian coordinates. There is no preferred coordinate system that dictates to me what I should use. So any way that I use of describing the energy of the system should not depend upon my choice of coordinates. So such descriptions, let me just give you this word, not because it will be very useful, but it's just a nice word to use. These descriptions must be covariant under the change of coordinates. That's just a technical term that is applied to these.
Covariant means the independent of the coordinates.
Covariant means that the physical description does not depend upon your choice of coordinate systems. Okay, so now given r is a function of u and v, I can define the vectors delta r by delta u and the vector delta r by delta v. And these are tangent vectors, to say tu and tv. Okay, they're tangent to the surface because they just say as I move from here to here, from 2 points across here, what is the direction in which my vector r changes. All right. They are not normalized. They are not required to be normalized because I am still working in the description of the u's and the v's. I have not gone to a description which requires them automatically, as we did in the polymer case, that requires that automatically makes them normalized. Okay. Given 2 vectors u and v that are tangent to the surface that I am considering at a particular point, I can always make another vector which is tu cross tv, and this vector is perpendicular to both these vectors because the cross product of 2 vectors is always perpendicular to both of those vectors. Now if I take this vector and I divide by the modulus of this vector, tu cross tv, then the vector that I will get, these are vectors, the vector that I will get is a unit normal vector. It's very straightforward. These are just simple definitions here of what this ought to be. This is the definition of the cross product. This is the normalization that makes this quantity to the right hand side a normalized quantity. So this is now the normal n hat at some point in the surface given by u, comma v. how do I find out the distance between two very close points on the surface? Suppose this is u, p, and suppose this is u plus du and v plus dv. What is the distance between these 2 points? So the way I would do that would be that we calculate r as a function of u plus du and a function of v plus dv. Let me subtract from this r as a function of u and v. And the modulus of this is the distance between these 2 points. Okay? So this is, let me call this dr is this object. So dr squared is just this object. First of all, I can take this and do a expansion about it. So the Taylor expansion says that this particular term here is r of u comma v plus delta r by delta u du plus delta r by delta v dv blah blah blah, and then minus r of u comma v, and this go away. So the only term that I have left is this particular term. Okay. So this is, suppose this is what we just wrote down. We call this tu. This we called it tv. So this becomes tu du plus tv dv dotted with itself. Okay. So this I can write as E times du square plus f twice f times du dv plus g times dv squared. And this quantity here is just mod of dr squared. But now remember, we did the same thing out here in looking at the infinitesimal distance between 2 points here. So this is just what we earlier called ds squared. It's just the distance internally on the surface between 2 points that are infinitesimally close to each other. Okay? And each of these terms here are the term E is T sub u squared, F is T sub u dot T sub v, and G is T sub v squared. It's just simple algebraic calculations here. So there's a quantity which I will just tell you briefly about now. It's called a metric, and that is defined as g squared minus eg minus f squared. And the metric is a somewhat useful object. And the reason it's useful is that this metric, which we call it G. G is just Tu cross Tv the whole squared. Okay, that you have to work out. And what I would like to sort of remind you of is the fact that if I have two vectors here, let's call it any vector, vector A and vector B. A cross B modulus is just the area over here enclosed by this element. It is spanned by A and B. It's an infinitesimal area. So A cross B squared is the area squared. This you need to probably remind yourself a little bit. Let me just remind you of how this came. So let us say we have a triangle here. The triangle here is, so let's just see what's a good way of doing it. Suppose this is A and this is B. So A cross B is mod A mod B times the sine of the angle between them. Now, this, suppose the angle here is theta, then this point here, this must be something like B sine theta. B sine theta, correct? All right. So the area of this triangle here is 1/2 times the base times the height. So that is 1/2 times A times B sine theta. That's the area of the full triangle. And I'm just trying to see how to relate that to what I had just here. And I'm just wondering whether this is probably the right element, because it's twice the area of this thing. So that factor of 2 will probably give me the right value for that element. You can relate this to this, because this is just 1/2. So this area of this particular triangle is just 1/2 of A cross B. So the area proportional to A cross B is there. The factor of 2 may come in how you define this particular parallelogram. Okay. The reason for showing you this is to finally come up with the answer that the little area element on the surface, dA, is obtained by taking the square root of the g that I just defined and multiplying it by du and dv. Why is this useful? Because this says that given any surface that I say I parameterize by some r as a function of your u and v. Given any r as a function of u and v, the area, the little area element on that surface is given by the square root of g that I know how to calculate, the du and the dv. So the total area is just integral times dA. But realize what this has done for you. This says that irrespective of how I choose my u's and v's, whether I use polar coordinates or cylindrical coordinates or some other coordinates or whatever it is, this formula is valid in all of those coordinate systems. So it tells me given u and v, there is a different g factor for each of those systems that tells me what to calculate. The reason I might want to do something like this is, suppose I have some energy that is proportional to the total area. Okay? So that is some surface tension term, which is an energy per unit area, multiplied by the total area. So I might put a gamma sitting outside, and this quantity here would have the dimension of an energy. So this is one way of calculating for a complicated surface what is the contribution to the energy that comes just from the area. Now we have to go a few more steps beyond this to do other things. For example, now we have to figure out what is the same way in which you can write this thing with the du and the dv if I want to find the energy due to curvature. Remember that what we did with the polymer was to think about the curved polymer and find the energy associated with that, which came from semi-flexibility. Again, it will turn out in the context of these systems that curvature is the most important thing. And I must find a similar way of writing this expression that concentrates on the curvature. And this is what we will do the next time. Let us see. Next time is Monday.